All right, in this video, we are going to talk about and explore kind of something technical, just the different notations and kind of what they mean as far as how you could write a definite integral versus how you could write a Riemann sum. And there's potentially multiple ways you could write a Riemann sum and express those sums of those rectangles as an approximation for the area of region. And as you go through that limit process and as you have infinitely many rectangles, how you can then get the exact area of that region. So this kind of just has a little bit of notation and terminology, just kind of introducing us into this idea. It says, let us have some interval a to b, and it's going to be partitioned, split up into n subintervals by n plus 1 many points. And it says, okay, my left one, a, we'll call that x of 0. My right one, b, we'll call that x of n. And then we have all these kind of stepping points in the middle, where we'd have a sub 0 is the left side a, then the next x value would be x1, then x2, so on and so forth. When we just have those little different x values to move ourselves across the interval. And delta x would be the width of each interval, or specifically the width of any particular subinterval. Okay, for any sampling point, c of k. For c, you can just use x, doesn't matter. C is just some x value that has been plugged in. So if we were to draw something like this, where you have a is the left side, and then b is this right side. Remember, they could consider this to be x of 0, then that's x of 1, that's x of 2, so on and so forth. Then what we could do is within each interval, we would have a rectangle. The width of that rectangle would be delta x of 1 or delta x of 2, depending on the width of each rectangle. But the widths are going to be universal, so it really doesn't matter. The widths are going to be dictated by how many rectangles you have. But each little rectangle that you split up, right, it would have a width, the delta x, and it would also have a height. Whether you do the rectangle from the left or whether you do the rectangle from the right, it doesn't matter. But each interval has some sample point. I think these ones are doing them from the right. So we take this right x value, again, for this first interval, we take that right x value and we get the height by plugging into the function. And then that y value gives us the height of that rectangle. So here we go. That's our first area of our first rectangle. That's the height. That's the width. And then we'd move over to this next interval and we do it all again. We have the width, and then we have the height. The height would be f of c of 2. And then we'd have the third rectangle, which had the width, and then we'd have the height, which would be f of c of 3, so on and so forth. We have all these rectangles, areas all added together. That's my Riemann sum, right? Adding together, starting with the first one, going to the last one. And what we're adding together is the area. Each rectangle has a width, then each rectangle has a height. And c of k is just some arbitrary x value chosen to represent each specific kth subinterval. Okay, and we know in order to make this Riemann sum no longer an approximation, in order to make it match the exact area, you would need to go through a limit process. You would need not 20 rectangles, not even 200 rectangles. You would need infinitely many rectangles. So you would take this Riemann sum and you would apply the limit as n goes towards infinity, right? Adding together infinitely many areas from infinitely many Riemann sums. That's how we get the exact area, which is our definite integral, right? This notation right here, the limit as n goes to infinity, starting with k equals 1 to n, that is your integration symbol, right? That squiggly looking s stands for your infinite summation. Now, what's going to be a little bit different is instead of just saying, hey, f of c of k, right, to represent each x value across, as you move yourself across that interval, you could kind of change it so that you're always in reference to your starting point, right? So obviously this first rectangle, you could use a, or if you wanted to use the right endpoint, right, you could take a and you could add the width, right? This width is delta x, and if I did a plus delta x, that would give you c sub 1, right? That would move you over. If you start with a and you add in the step size, that would give you to this next point. And you could use this just as well as you could use c of 1. Or if you wanted, instead of using c of 2, you could go a, and then you could add 2 of the widths, right? So c of 2 would be equal to a plus 2 steps, and so on and so forth. This would be a plus 1, 2, 3 steps. The next one, CO4, would be a plus 4 steps. So you could change and you could rewrite every little subinterval instead of it just being c of k. If you wanted to put it back in terms of your reference point, the left side a, and then also in terms of the step size, you could rewrite each little x value, c of k, you could rewrite it as a plus delta x of k, and that k value would just change depending on how far across, how many steps you would need to take to get from your left side a to that arbitrary representation of your subinterval. All right, so that's a little bit weird. The C of k, just think you could rewrite any C of k by doing a plus a certain number of steps. And that delta x of k is how many steps you apply. Alrighty, so let's go ahead, and of course you have the heights, the widths, add them all together, infinitely many. That's your definite integral equivalent. Now, we're going to go through, and this is a little ticky-tacky of a lesson. So, yeah, I'm going to go through. I changed it up. This is going to be different than what I've done in the past. Hopefully it still makes sense, but this is not something that's super easy. But I will plan on doing some of the homework questions together with y'all in class, because actually doing the questions isn't too bad, but understanding the development of this notation and why it is the way it is, it's a little bit tricky. Okay, so try to bear with me, but remember, we're going to go through some examples, and I'm going to show you exactly what I want you to do and what you're going to have to do on the AP exam, the conceptual kind of background behind it. If it makes sense, wonderful. If it doesn't, it's not the end of the world. You just have to be able to answer the questions at the end of the day, and that's going to be pretty doable. All right, well, let's go through and let's develop this notation. This is earlier in this unit, we learned how to approximate the area bounded by a function and the x-axis by writing a Riemann sum. And suppose we wanted to write a Riemann sum to represent the area bounded by y equals x to the fourth between x equals 5 and x equals 8. This diagram is not going to be to scale, but I'm going to draw it in such a way so that my limited art skills will be fairly okay. Okay, so we have this function. Remember, that function is y equals x to the fourth, or if you want to say f of x equals x to the fourth, that's fine. And then we would be looking at this area. Let's say the left side. We'll put this left side, x equals 5, and then we'll put the right side over here. We'll say this is x equals 8. So we'd be trying to write a Riemann sum that's going to represent this area. So what I would do is I would take that region. Well, here it tells us, it says draw a vertical line at x equals 5. Okay, done. And at x equals 8, done. Awesome. And draw subintervals beginning at 5. So we're going to split this up. We could do like the first subinterval, and then we're going to have a universal width. So try to draw them equally spaced. There's my second subinterval. Here's my third subinterval, so on and so forth. And then we could get all the way to this last one, right? And then dot, 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 right? The ellipses mean continue on with that same pattern. And then within each one of those subintervals, I could do a rectangle, and I could add the areas of those rectangles together as an approximation for the area of that weirdly shaped non-geometric region. Right, let's kind of go through this notation. It says the width of our interval is, well, the difference between 8 and 5 is 3. Now, we want to split it up, and we want to have n many rectangles, right? So if the width is 3, and I'm going to split it up into n many rectangles, that means the width of each one, delta x, will be 3 over n. Right? We have n many rectangles, so if my total interval width is 3, divide it up, split it into n many parts, that means the width of each part is going to be 3 over n. Right? So this little width is 3 over n. This little width is 3 over n. Right? All of these step sizes, all of these widths for all of those little subintervals would be 3 over n. You take that region, which is 3, divide it into n many pieces. That means each piece is 3 over n. Now let's use that. We're gonna talk about, hey, this x value that we start with, 5, and then my step size is 3 over n. I want to use those two facts to kind of get some way to describe this first point. All right, so my first subinterval would have its right endpoint at. If I start at 5 and I apply one of the steps, that would be 5 plus 3 over n. That's how you could describe that first subinterval's right side. And then similarly, if you took another step, right, you could do 5 plus 3 over n plus 3 over n. So that would be 5 plus 3 is 6 over n. That is what you could use to describe that second point. 5 plus 6 over n. And then we could continue on with this process until we got all the way across the interval. The next one would be 5 plus, let's see, 1 step, 2 steps, 3 steps. You'd have 3 over n plus 3 over n plus 3 over n. That would be 5 plus 9 over n. Or if you want to think about it like this, it's 5 plus 1 of the steps. Then it's 5 plus 2 of the steps. Then this one is 5 plus 3 of the steps. Right, so you could rewrite it with the 3, 6, 9, or the 1 times 3, 2 times 3, 3 times 3. It doesn't really matter. But we would continue this process until we would get all the way to this last one. And that last one has its right endpoint at 8. But we're going to be writing this as a sigma notation. And whenever I write something in some type of a sigma notation, I want all of the terms to look similar. I want them all to have the same basic format. So instead of 8, check it out, I'm going to rewrite that as 5 plus 3. Okay, that's the same thing, right? 8 is 5 plus 3. But I want it to look something more like this, where it's 5 plus something over n, 5 plus something over n, 5 plus something over n. So I'm going to take this 8, which I've rewritten as 5 plus 3, and I'm going to rewrite that as 5 plus 3n over n. That would be the same thing as 8, right? The n's would cancel. 5 plus 3 is 8, right? There's nothing really different with any of those. I'm just rewriting it in a slightly different format, right? Mathematically, all these things are the same. All right, so that would be 5 plus n many steps, with each step size being 3 over n, right? To make it fit the same type of a pattern. Now, if we want to write a Riemann sum, right, we'd have the rectangles for all of these little regions, using the right side, I guess. So we'd use this first height. Let's do the widths first. So the width of this first rectangle would be 3 over n. And then the height of this first rectangle, we'll use the right Riemann sum. So I'd use the right side of that interval, and I'd plug it into the function. So I'd take this x value. Remember, your function raises it to the 4th power. So 5 plus 3 over n to the 4th power. That would be the width of the first rectangle. And then taking your x value, your right endpoint of your first interval, and then plugging it into the function, so raising it to the 4th, this would be the height of my first rectangle, right? So this is the area of my first rectangle. Then I could do something similar to get the area of this second rectangle, right? We'd plug it in. The width of that second rectangle is 3 over n. And then to get the height, I would plug in this value, or I didn't write the 5 plus 9 over n, did I? You would plug in the next value, right? The right side of that second interval. I'd plug in this value into the function, so I would have 5 plus 6 over n to the 4th power. That would be the height of the second rectangle. That's the width of the second rectangle. And then we could keep doing this same process to get all of the different areas of all the rectangles. The third one would have a width of 3 over n. And then the height would be 5 plus 9 over n, all to the 4th power. And then plus ... let's skip. And then the last one we could rewrite. Instead of 8 to the 4th power, we'll have 5 plus, or not 5 plus, I forgot the width. We'd have that 3 over n, which would be the width of this last rectangle. And then instead of using 8, right, so this width is still 3 over n, but instead of using 8, I'm going to make the 8 look like this. So it's going to be 5 plus 3n over n to the 4th power. And there's your Riemann sum. The width of the first rectangle, height of the first rectangle. Width of the second, height of the second. Width of the third, height of the third. So on and so forth until you get to that very last one, which also has the same width and then has a height. And then what's nice is when we have this universal width, we could factor that sucker out to the front. So 3 over n, and then everything else is going to be left over, right? So it's just all this stuff, but the 3 over n's are factored out to the front. So I'd have 5 plus 3 over n to the 4th. Then the next height would be 5 plus 6 over n to the 4th. Then the third one would be 5 plus 9 over n to the 4th. The next one would be 5 plus 12 over n to the 4th. Then continuing on. But I'm just going to do plus ... At least write 2, right? I like to see 3 terms. Then you can put the ellipses to continue the pattern. I like 3, though, the most. Then we get this last one, 5 plus 3n over n. There we go. Right, so there is my Riemann sum. I got the universal width. Then I have the heights of all of those rectangles. Remember, you take the x values, plug them into the function, and what that function was doing was it took your x value and it just raised it to the fourth power. Right, so don't forget, it's not just the x values. You have to take the x value and do whatever the function tells you to with them. But this is my Riemann sum. That's only an approximation, no matter if you have, if n equals 10 rectangles, right? That's an okay approximation. If n equals 100, that's probably a good approximation. But how we get it exactly is we're going to take the limit as n goes towards infinity, right? You have infinitely many rectangles. That's how you can get the exact area. So what definite integral would give us this exact area? Well, we know this. Be the integration from 5 to 8. Of x to the fourth dx. So if I were to have this Riemann sum, and if I were to take the limit as n goes toward infinity, that would be the exact area. But the definite integral also gives us the exact area. Therefore, hey, if all this stuff with the limit gives me the exact area, and if this gives me the exact area, the transitive property of equality tells me that this definite integral notation is the same thing as the Riemann sum. So it's the same thing as the limit as n goes towards infinity. You have that width factored out, 3 over n. Then we have the rest of the Riemann sum, 5 plus 3 over n to the fourth. Plus 5 plus 6 over n. Am I on the screen? Ooh, good thing I caught it because I was just barely off the screen, wasn't I? Right, I'm just rewriting this same Riemann sum with the limit because that's the exact area. Plus 5 plus 9 over n. I'm glad I looked up. Plus dot dot dot, the last one. 5 plus 3n over n to the fourth. Okay, did I squeeze it on the screen? Yeah, I did. Okay. So since this, remember, this is the Riemann sum, which we did a couple steps ago. You have the width factored out, then you have the summations of all the height. That's an approximation. Whenever you have the limit, though, that makes it exact. So this is the area exactly. The integral is also the area exactly. So transitive property tells me those two things must be the same. This integral is equivalent to this Riemann sum. Now, why would anyone choose the Riemann sum? I don't know. Right? The integral symbol is much nicer. But those two things mathematically will give you the same thing, right? The exact area of the region, the exact area of the region, right? It's just easier to do the integration with the calculus than to do all this geometry and the Riemann sum process. All right, next what we can do is, hey, that's what I consider to be expanded Riemann form. Expanded Riemann form. Riemann. And what you notice about the expanded Riemann is it's only based on the variable n, right? So only n's in that expression. But that expanded form isn't how the AP exam is going to test it. It's how they used to. This Riemann sum notation stuff, it used to be on the AP exam. Then they took it out and they didn't test it. And everyone was really happy for a couple of years. But then a handful of years ago, I think it was 2017. They added it back. They're like, hey, surprise, here you go. We're giving back everyone's favorite Riemann sum notation. But the way they used to change it, or the way they used to test it, which was this expanded notation, they're like, oh, curveball. Now we're going to test it with a different notation. Instead of it having all expanded, we're going to collapse it, and we're going to condense it, and we're going to write it with a sigma. Okay, so let's look at how we could do that. This integral is still the same thing. But we're going to collapse and condense this sigma. Now, we'd still need the limit. That doesn't change. And we still have this width, the 3 over n. That doesn't change. What gets collapsed into the sigma is this summation, right? Because the sigma is a summation, right? So I have this first term, second term, third term, fourth term, dot, 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 all the way to this last term. Since all those terms have the same basic formula, I could collapse them and write them as a sigma. Now, let's start with the first one. Then I'm going to have to figure out what's the last one. But then each one of those terms fits this same formula where it's 5 plus something over n, right? 5 plus 3 over n. 5 plus 6 over n, 5 plus 9 over n to the fourth, 5 plus 3n over n to the fourth. So every one of those terms, that's why instead of 8, we wanted it as the 5 plus 3n over n. That's why we wanted them all to be the same form so that we could collapse it to this sigma. Now remember, that was like 3 times 1. That was 3 times 2. That was 3 times 3. This is really 3 times n. You took one of the steps. and the step size was 3 over n. You took 2 of the steps, the step size was 3 over n. You took 3 of the steps, the step size was 3 over n. You took n many steps, and the step size was 3 over n. So if you wanted to rewrite this in a condensed sigma form, you need a k, that integer, that kind of notation that's going to step you across the interval. It's the index. We want k to start with 1, then k to start with 2, then k to be 3, right? So when I'm writing this, we would have 5 plus 3k over n. And then if you plug in 1, it should give you the first one. If you plug in 2, it should give you the second one. If you plug in 3, it should give you the third one, right? And then if you look at this very last one, what would the upper bound be? N. You'd have n many rectangles, and then you take the limit as n goes to infinity. Okay, so that's a different Riemann sum, right? This is another Riemann sum. This is what I consider to be the condensed Riemann sigma, and I'm going to say with calculus because we're about to have another Riemann sigma that I call with geometry. So there's 3 different types of Riemann sums, and I'm like, oh my gosh, Mr. Bell, why are you doing this? I'm not doing it. The AP exam is doing it. Blame College Board. But to differentiate between the different types of Riemann sums, I created names, right? The expanded Riemann, that's not an official name. That's a Mr. Bell name. The condensed Riemann sigma with calculus, that's not an official name. That's a Mr. Bell name. Okay, but it helps me to differentiate between the types of Riemann sums that we could see. We have the expanded form, which is only n's, right? And it's expanded. Then we have the condensed sigma, but it's with calculus. It's got k's and n's, right? It has with k's and n's. Now, there's a more geometric way that you could write it, and I could express this definite integral one more way, and I think the geometric way is the easiest way. Right? We'd still be adding together rectangles, and we'd be starting with the first one, going to the last one. But you still need infinitely many too, right? Don't forget about that. But for the geometric notation, what you're going to see is, hey, instead of this, they're just going to say something like a delta x of k, and then for the height, then you would have just 5 plus your c of k, or I guess for this one, instead of the x, let me flip it back. For the geometric notation, instead of using the 5 plus the step size or whatever, you can just use c of k. We can use c of k to represent that arbitrary subinterval. So I could write this one more time. Let me get this a little bit closer because we don't need it that far. The integral symbol, remember, it's adding together infinitely many things, right? So the integral symbol is all this, wonderful. But instead of x to the 4th, you could rewrite it as c of k to the 4th. That just represents your arbitrary x value for each subinterval. And then instead of the dx, you could change it to a delta x. If you want to put the k, that's fine. It's not necessary. So this is what I consider to be the condensed. Am I on the screen? Yes. The condensed Riemann sigma with geometry. Okay, and a couple of things for this notation. For the condensed Riemann sigma with geometry, you just straight up change the x's to c of k's, right? Change the x's to c of k's. You change the dx to the delta x. If you want to put the k, that's fine. But what's also important is right now, we don't really know what part of the graph we're getting the area under. I can tell that it's the x to the 4th function, right? There's the height of all my rectangles. There's the width of all my rectangles. Here I'm adding them together, and there's infinitely many. But nowhere in this notation does it tell you what part of the graph we're finding those rectangles underneath, right? The integral symbol is all of this stuff. The x to the 4th is this stuff. The dx is this stuff. But the 5 and the 8 don't translate anywhere into this geometric notation. So for this geometric notation, you have to kind of declare what the interval is. So you could just write 4, 5 to 8. Make sure you always put 4, A to B. You have to tell me what part of the graph. So we have the 3 different types of Riemann sums. I know, they're not fun. It's tedious. But we have the expanded Riemann sum, which is like this, where it has only the n values. Remember, all the Riemann sums need infinitely many rectangles. So all of them have that infinite limit as n goes to infinity. But we could have that expanded notation, which is only n's, or we could have the condensed Riemann sigma with calculus. That one's got k's and n's. Or we could have, which I think is the easiest, we could have this geometric, this condensed Riemann sigma with geometry, which, I don't know, you just always have to make sure you define what part of the graph. But we have three different but equivalent Riemann forms, Riemann sum notations that we could use to translate this integral over into, right? This one integral is equivalent to all three of these different Riemann sums. So it's tricky, right? How do I know which one you want? Well, expanded Riemann, again, that's Mr. Bell words. That's the one with only n's. The Riemann sigma with calculus, that's the one with k's and n's. And then the condensed Riemann sigma with geometry, that's the ones where you change the x to c of k, you change the dx to the delta x, and then you have to declare your interval. You have to say for a to b. We have the three different Riemann sums that all represent the same definite integral. So there's the four notations, right? There's the integral, which there's only one way to write the integral. Hallelujah. But that one integral, you could rewrite it as multiple different but equivalent Riemann sums. So we got to be able to know all three of them. If I'm given an integral, you should be able to produce all three of the Riemanns. Or if you're given one of the Riemanns, it doesn't matter. If you're given the expanded, you should be able to translate it to the integral. Or if you're given the condensed with sigma, with calculus, you should be able to condense it to the integral. Or if you're given the geometric one, you should be able to switch it, right? If you're given the one integral, you should be able to write all three of the Riemanns. Or if you're given any of the Riemanns, you should be able to switch it, right? Or if you're given that, you should be able to produce the other Riemanns, or that. There's these four notations, the one integral, and then the three Riemann sums. Whichever one you start with, you should be able to produce the other three. And it's tricky and it's tedious. This is the one that's the most important, because that's the one that the AP exam is most likely going to test you with. This is how they used to test it. This may come up, the geometric one, although I think it's less likely. This one right here, the condensed Riemann sigma with calculus. Again, that's not an official name. That's a Mr. Bell name. This is the one that you hopefully can understand, because that's the one that's most likely to come up. All right, I got to end this video because I got to go teach my class, but I'm going to make another video with me doing a couple of examples, and then I'm going to do probably one or two from the homework for you as well. So please watch the next video as well.